Howdy everyone, my name is Daniel, and it is currently 3:27 a.m., but I was just dying to show you guys everything about Quaternions, so I spent about a whole day researching, following this really good tutorial, I think like an OpenGL website, breaking down the linear algebra and how you can write this whole library of functions to work with Quaternions, uh, so that I could show it off in Unity. And once I got into Unity, I realized, wow, they did this all already. This is really well abstracted. You really have to know almost nothing about quaternions to be able to work with them in Unity. So I guess that makes my job a lot easier and it makes this video a lot shorter. Um, so our goal today is basically to make this. This is just smoothed rotation in 3 dimensions. So you can see our little uh, what would that be? Tetrahedron has nice. Well, I haven't even been showing off the 3-dimensional aspect of it. Good tracking here. I still can't, for the life of me. I know this guy's a tetrahedron. What the heck is this guy called? Well, we'll call it a pyramid for now. And the secret of that is in this smooth rotate function. So in a bit, we'll get into how we go about starting and writing this. And so to start with, let's look at the scene setup. These guys, well, that's removed now. Just have the rigid body on them, nothing else. The rigid body is important on this one because that's how we're going to be rotating it. One of the importances of actually using quaternions instead of like Euler angles or whatever, or just setting the rotation in the transform, by the way, let's call this smooth rotate, is that you can actually feed that information into the rigid body so that it can do physics calculations with it. So you have stuff like collision and friction. Wait, comments. So to start with, let's set up some member variables. We're going to need the initial rotation, which will be easy enough to get. Let's see, let's define a max speed in degrees per second. Let's see. Yeah, let's just call this speed. And we want a smoothing factor, so let's say if it's within an arbitrary amount, let's say a threshold 10 degrees. If it's within 10 degrees of its target, let's start slowing down. And we could lerp, but I actually don't really, I don't know, I don't feel like lerping would be quite right for this. I kind of want to do an inverse or inverse square type relationship. So if we're 1 degree away and our threshold is 10 degrees, let's try moving it 1% the speed. I feel like that might give us more of a snappy rotation as opposed to a slow one. And other than just having a smoothly rotate from point A to point B, let's also have a constrained rotation function. So the reason I want that is because a lot of things aren't supposed to rotate along any axis. So if you have like a camera on the wall, or if you have like a turret somewhere, or even a player character, right? They're not supposed to spin about their waist head over heels. You want the rotation to be a bit constrained. So we'll have a constrained rotate function that figures out what it should be doing in an unconstrained rotate function, which is just going to do like what you saw in the scene just there. But before all that, let's just try using quaternions to just print what's the angle between me and where I want to go. So to get there, to be our first little test case, let's define a transform, and this will have to be public. transform that we want to track. We also want this float. Well, what do we call this? Slow down angle. Do we need anything else? I don't think so. Okay, so let's get started. And the rigid body, well, and start, the first thing we want to do is get a reference to the rigid body. So we're going to say body equals get component rigid body. We're going to say our initial is body dot rotation. These two should be public. Is it? Oh, that's the wrong thing. There we go. Control Alt Shift. So those will set themselves, and that should be good. Okay. So we want to print our difference from, let's say, our transform.forward and our offset from the thing that we're tracking. So we want to aim our transform.forward at the thing we're tracking. So let's take a look into this thing. What do we have? Look at that. That's between two rotations though, and we don't necessarily have the second rotation. We could try that though. Let's take a quick look through everything though. That could be useful for a constrained movement. Appreciated. Dot products. Dot products are just mathematical adding and multiplying. Create one from Euler angles. This one will take a vector in one direction and give you the quaternion that rotates it to another direction. And this one gets you the inverse of a rotation, so I guess the reverse of it. We can lerp between them. We can get a look rotation, so if we define a vector 3 that's supposed to be up and a forward, which I imagine should be perpendicular to each other, you get the resultant rotation that it has to be at. And slurp is probably one that you haven't seen before. It's spherical linear interpolation. This is just a nice way of actually lerping between two quaternions, not just mixing their values together. It will keep things nice and sensible. So for now, it seems like our best bet is that angle function. So we want our first one, which is just initial, and our second one. So our best bet here, from our quick look over things, seems to be that look rotation. So we want our forward and our upward. For our upward, we'll just say it's our current one, right? Our transform.up. Assuming that, the thing we want to rotate to is not directly above us. We could be more careful about that. For now, let's see if that gives us bugs later, but we'll try it like this for now. And our forward will just be its position minus our position. Track.position minus transform.position. And let's give this a test. So we're going to have to move this thing to the side or something. Right. Oh, I didn't even print it out, did I? There we go. Still no? Oh, I'm a fool. I didn't even attach the script. Well, we don't need that yet, and we'll be tracking this guy. And what do we get? 33.3 degrees. Do we know that's right? I don't know, let's eyeball it. Seems close enough to me. Alright, so now let's make some function prototypes for our constrained rotate and our unconstrained rotate. So let's say that and void unconstrained rotate. Unconstrained rotate should take a position that we want to go to. So let's say vector 3 target and unconstrained rotate, or oopsie, it should take this. Yes, both of them should take a target. But constrained rotate should also take an axis that we want to rotate along. So if this were a person, this would be the y-axis probably. If it were a wall-mounted turret and the wall was in front of you, it would probably be like the z-axis. It would be its own transform dot up. So let's see, vector 3 normal axis. So let's start with unconstrained rotate, because that's probably a little bit easier. So, okay, so let's logically think about what we have to do here. So the first thing we're going to want to do is figure out what's the angle of rotation that we have to do to get from A to B. And the reason we want to do that is so that we can apply our maximum speed and our slowdown angle. So first order of business is getting that. I guess before that, though, we kind of need to have the quaternion that represents where we're rotating to, but luckily enough, we already figured that out. We can use this for it, though I don't think we will, because this is unconstrained rotate, and this one kind of has a constraint built in, right? We have to maintain this transform dot up. So instead, what we're going to use is, let's see, Quaternion dot from to rotation. This takes a vector 3 that points in one direction and a vector 3 that points to another direction. Again, gives you the quaternion that rotates you from one to the other. So our first one is just going to be our current rotation. And our other one is going to be the offset that we have from our target, but normalized. So track dot position minus transform dot position dot normalized. Oh, right. This is supposed to be a vector free. I just explained that. We'll use our forward. So the reason I call this full is because it's the entire rotation necessary to go from A to B. So we can get our angle of that. We'll say angle. Is that already defined somewhere? Oh, okay. Just VS Code being a little weird on me. And we're going to say that's equal to Quaternion dot angle. Now, we have something here that is a little bit interesting. See, this represents a change in rotation. This isn't like our final rotation. So we could do like the angle between our initial and our initial composed with the rotation that we want to apply to it, which would just be like body dot rotation and then full times body dot rotation. But you can see this is a little bit repetitive, so what we can actually do is we can use Quaternion Identity. And when we say identity here, it's actually a lot simpler than it sounds. Just like the identity principle in math, identity is just another word for one. It's kind of like your default, your zero state or one. So you can effectively just divide out your initial rotation from both sides, and you wind up with a 1 here and full on the other. Easy enough. And now we have that angle, so we want to figure out, is that too much? So let's say float. How much we're actually going to turn here. So is equal to, let's say, so if we're greater than speed, we want it to be speed. If we are less than speed, also speed. If we're less than the slowdown angle, then we want some formula. So really the only thing we have to compare against is the slowdown angle. So angle greater than slowdown angle. And this is a ternary statement, so it'll do the thing on the right if it's true, the thing on the left if it's not. If it's greater than slowdown angle, we do speed. If it's not greater than slowdown angle, we'll do, let's see, angle divided by slowdown angle. Now this would be the linear thing, but we want the square root of that. Both would look smooth. I just kind of feel like doing it like this. Oh, of course, can't forget to throw in time.delta time. Go right here, and time speed times delta time. That should be good. Now that we have the actual angle that we want to turn by, there's a nice little quaternion function that again handles this for us, and that's quaternion.rotate towards. So let's call this delta. And we have a starting quaternion, which is just our body.rotation. Our final one, which I guess we have to, or you know what? No, we can do it like we did above. And then do turn, and we'll get a quaternion that rotates us in the direction of full by at most turn degrees. And last thing we have to do here is actually tell the rigid body, hey, rotate. So that's real simple. That's just body.move rotation, and this is more or less, this is a set function, not just we throw in a quaternion and it rotates it by it. So we have to do the multiplication, which is just body.rotation, and we have to apply this afterwards. So delta times body.rotation. Something to note with quaternions and matrices in general is that multiplication is not commutative, so the order matters. And if you're wondering about the reason why for that, you can just kind of think about it like this. Like if you point your finger forward, and you have two rotations here. If you have like rotation 90 degrees upwards, I guess relative to your finger, and a rotation 90 degrees to the left, these two things happen, they put you in different places depending on what you do first. If you do up and to the left, you end up pointing left. If you do left and then up, you end up pointing up. In a kind of weird way, but order matters here. So with these guys, the one on the right is what is effectively applied first. This, you can kind of think about it if you moved it like from your first position, your 0 state, to body.rotation, then you're at the rotation that you currently have, then delta, the rotation that we're moving to. So this should be our unconstrained rotate function, though knowing me, it probably did something wrong here. But we'll have to debug it to see. So let's for now just say unconstrained rotate to track dot position. And let's set a max speed of 90 degrees and a slowdown angle of like 30. Hey, that looked pretty nice, didn't it? Let's see. Oh yeah, it even spins around to get there. Wow, first try, that's a record on this channel. Whoa. Okay, so now that we have this, our constrained rotate is actually not very difficult. For this, we're going to use a plane construct. So let's say plane, I don't know, what do we call this? P equals new plane. And we're going to define this. Why are you giving me two vector 3s? That's weird. Give me a vector 3 and a quote. So I'll type this first and then explain it after. Dot between axis and our position. Yeah, that's fine. Also, let's make sure our axis is normalized, because I think that might do something stupid if it's not. It might just normalize it on its own. But might as well keep things consistent in the code. So the way a plane is defined in mathematics is by its surface normal. By that, I mean a vector that points perpendicular to the plane at all points. It also needs one other thing. It needs its offset along that normal from the origin. So if you had a plane that was like a dinner table, set out in front of you, and it was 2 meters up off the ground, your normal would be 0, 1, 0, in other words, pointing straight up, and your D here would be 2 meters. So what I did here was I dotted our current position and the axis that we're constrained to. And that gives us our projection onto the plane. It'll be a little bit easier to visualize if I put something in here to visualize it with. But that is how we get this plane. And we're going to say target equals plane dot, or sorry, P dot closest point on plane. There we go, nice and easy. To target. Oh, you know what? I might have to make this negative. We'll see if I have to make this negative in a bit. Might have to be negative. Just for math reasons, I think. And from here, we just pass this to Unconstrained Rotate with our new target. Oh, right. Yeah, that's fine. And now we'll do Constrained Rotate, and our target is just track.position, and our axis is, let's say, vector 3 dot up. Let's give this a spin. So what we want to see is our, I still don't know what this thing is called. What is this thing called? Dang it, why didn't I name it? It is not an octahedron. What we want to see is this thing not rotate up when I move the octahedron up. And it rotated up. And it rotates down. That is not what we want to see. So let me try making this negative. Alright, figured it out, I'm a fool. I used track instead of target, which is the argument to the function. Let's see if I use track anywhere else. I don't think I did. Okay, cool, this should work now. Let's undo this negative so we can actually do debugging step by step. Okay, promising, very promising. Hey, would you look at that? Now, I still want to see something. I want to see if I move this guy up, should not rotate down like that. Okay, he does. Yeah, we don't want that. Because, let me explain why. The way we set this up, we want it to only rotate on the y-axis effectively. But when I start it right now, it's going to rotate down and look at it. There it is. And the reason for that is because our plane is not set up to be on the body. So if we fix that, in other words, you could imagine the plane that we were projecting it against was in this zero plane. It was not up here with our object. But now when we made that negative, it should be up here with our object. I wish I could tell the gizmos to figure that out in Unity, but that is not a thing gizmos have. Draw mesh. And here we go. Now it is working like we want. So let me know if you want me to implement the entire Quaternion class in Unity, because that's kind of what I prepared for, but it ended up being real easy. Like, comment, subscribe, whatever YouTubers say, and have a nice day.